Okay.
Yeah, I got you.
If I go, it's mixed.
Thank you so much.
Welcome to another PAS Colloquium. It's a real pleasure to have here Daphne and Dusty. We're going to be talking about the irreversibility, current fluctuations and certain situations in the quantum. Daphne, joined us as an associate professor very recently. He got his PhD from the University of Sao Paulo in 2012. He was an assistant professor in the Universidade Federal do ABC, something there. And then he was also a professor at the University of Sao Paulo. And now we have him here. So Gabriel is a very accomplished scientist with a number of papers published in a very short order, especially in the last 2 years. It is like 60 papers or something. And he's also a very, very careful mentor. So from what I understand, we have a mentor. He's 2 postdocs, 4 graduate students, and 14 master students.
Yeah.
So he's new. If you're looking for both people to work with, he's a great person to work with. And thank you so much for the stuff. We're excited to have you here.
Yeah, thank you so much. Thank you. Thank you for the invitation, and thank you everyone for showing up. It's really a pleasure to be here. Let me see where I should stand. Probably over here. Okay. Yeah. So I really appreciate this opportunity to try to explain a little bit about my research. The things that I love to do, and also I'll try to explain a lot about what I'm interested at this moment. So right now. So let me see if I can get this working. Yeah. Okay. So I actually wanted to start this talk with a small game. So I'm going to show you a series of 4 videos, and I want you to try to guess if the video is being played backwards or not. So let's see. Let's start with this one. So any guesses?
I say not.
Not. Okay. Yeah. So let's do another one. Definitely not. Yeah. Hard to tell, I guess. And finally, this one.
Did you have a little lag?
So these videos are by George Porter, who's a Nobel Prize winner in chemistry. He has a series of very nice lectures on thermodynamics on YouTube. And they introduce the notion of the arrow of time and irreversibility. So how do we think about a process being irreversible or not? So ultimately, the way that I like to think about irreversibility is exactly like in those videos, comparing a forward process in a natural order with the time reverse, with the backward process, and essentially comparing how likely is to observe the backward version compared to the forward one. So, for example, the videos that we saw that were clearly being played backwards were exactly those which had a lot of dissipation. Like, for example, a coffee mug falling, right? You lose a lot of energy, a lot of heat. And so there's a lot of dissipation, and so it's a very irreversible process. So if you play it backwards, it looks very different. And those that we couldn't really tell, there was very little dissipation. So this is kind of a very, at least in my opinion, profound idea, but really cool idea about how we interpret irreversibility. But it also leads to the question that as to why does this happen, because Newton's law, Schrödinger's equation, and so on are time reversible. So if we just integrate Newton's equations of motions, and if you play it backwards, we get exactly the same thing. So why do we get irreversibility for? Where do we get it from? And I really want to push forward this idea, this operational definition that I call it, which is that you need to think about what is accessible and what is not. So for example, if your coffee mug falls, there's heat that is dissipated to the environment, and that is lost, right? That energy is lost. So since you cannot never recover it, then there's some elements of your problem which are just not accessible to you. And whenever you have something that is not accessible, that's where irreversibility comes from. So let me try to explain that idea in more detail. But to do that, I will actually have to connect irreversibility with a different concept, which was introduced by Clausius, called entropy production. So this idea that I just showed you about looking at a forward and a backward process, this is much more modern. We're going to come back to it. Clausius, during his days, he thought about it in a different way. He thought about it in terms of this notion of entropy being produced. So here's a little bit how it works. So I'm going to consider standard, second-year thermodynamic scenario. We have a system. It's connected to heat baths, which can allow heat to flow. There's like a hot bath and a cold bath, and you can also extract some work from it. There's like an engine or something like that. So very standard thermodynamic scenario. Now, the first law of thermodynamics will give you a balance equation. It's going to tell you that the energy of the system, if it changes, it can change either because work was injected or extracted, or because heat was injected or extracted. So it's just a balance equation. According to Clausius, entropy should not follow a balance equation. So if we look at how the entropy of a system changes, there will be a part which is like a balance equation. So these two terms, they're called entropy flows. So the entropy flow is the heat flow divided by temperature flow. However, there's also an additional term, which is not a flow. So I would call a balance equation like this part up to here. I would call it a balance equation because the change of one thing is flows coming in and out. But there's also an additional term, and that is called the entropy production. And this entropy production is always larger or equal to 0. And this is a fundamental term which actually defines the second law of thermodynamics. So the second law can actually be stated mathematically as just by saying sigma is larger or equal to 0. And I personally like this very much because I always had trouble in my undergrads in thermodynamics classes because people would formulate the second law in words. And I also always found that a little bit weird. We are always used to working with equations, and the second law is given in these statements like heat can never pass from a cold body to a hot body, blah, blah, blah. It also felt a little bit weird that we had the second law written in words instead of just as an equation. But we can formulate it as an equation, and it's just this inequality, sigma larger or equal to 0. And let me actually show you how that can be used in practice. And I think this is really cool. So I hope everyone can see it down here. So let's consider a cyclic operation, a steady state operation, where the energy of the system no longer changes and the entropy of the system no longer changes. So I'm going to equate these two to 0. So this is just a statement that even though the process is cyclic, there's still stuff happening. So there's still a balance, work converted into heat and vice versa, and entropy production is converted into entropy flux and vice versa. Okay, so these are the tools at our disposal. So let's first look at a heat engine. So a heat engine, the efficiency of the heat engine is work divided by hot heat. And if we just, play around here, just, move things around and isolate some terms in these equations, we can actually rewrite the efficiency as the Carnot efficiency minus a positive term, proportional to the entropy production. So this is why, this inequality, sigma larger or equal to 0, tells you why we never reach Carnot efficiency. We don't reach Carnot efficiency in an engine because we produce entropy. And the mismatch between the efficiency and the Carnot efficiency is exactly given by how much entropy you produce. So I think this is like a beautiful way of stating, in this case, it would be Carnot's statement of the second law, now written in terms of the entropy production. Okay, here's also another example. Suppose we don't have a system in the middle, we just have heat flow, right? So there's just a hot body and a cold body. You can imagine this is, your frying pan, and this is, the water coming out of the sink, and you just put them in contact. Now, in this case, the first law is just going to say that, the heat flowing from one body is minus the heat flowing from the other body. So this equation is going to give us this inequality. Now, this is, I think, explains very well why the second law can be so powerful. So this states that, the product of these two things has to be larger or equal to 0. So this means that the sign of this thing has to match the sign of this thing. So the sign of the heat is going to match the sign of this difference in temperatures. And this is the statement that heat flows from hot to cold. The sign of the heat flow will always match the sign of the temperature gradient of which system is hotter and which system is colder. So this is how Clausius formulated the second law. Essentially say that heat will always flow from hot to cold. Okay, let me just give you a couple more examples. Another one, and I want to kind of give some examples and try to show you a little bit of current research that we're doing right now, how this kind of merges into present day research. So one very famous principle, which also follows from the second law, is called Landauer's erasure principle. And this is, it essentially establishes how much does it cost to erase a bit of information. So Landauer used to work at IBM, and he was interested in, the thermodynamics of computation. And what he discovered was that there is no energy cost into writing information in a bit. So if you want to write a bit of 0 or 1, there is no cost in writing the information. But there is a heat cost in erasing the information. So when you want to erase it, then you pay kBT log 2. That's a fundamental cost. And this follows again directly from the second law. It's just the same inequality that we had before, sigma larger or equal to 0, applied to this process. One of the questions that we've been asking that I think is quite interesting is, what happens if T equals 0? This is quite relevant because there's no such thing as 0 temperature, sure, but many processes, especially like in quantum computation, they occur at very, very low temperatures. So, I mean, does the bound trivialize at low temperatures? Because, I mean, does it just mean that there's a the minimum heat cost is 0, or is there still a fundamental minimum cost that you have to erase information? So we're playing around with waveguides. So and this is very relevant to modern quantum computation. And we saw that there is still a fundamental heat cost if you use a waveguide, and you get a new bound. You have to rederive some results, and what you get is kBT log 2, which is the same as Landauer. Plus, you get a temperature independence correction, which is therefore the only term that is going to remain if you are at 0 temperature. So this is interesting. It tells you that there's really a fundamental heat cost even if you are at 0 temperature, and shows you a little bit how you can actually use the second law to make predictive to make predictions.
What is L?
Sorry, so L is the size of the waveguide. Yeah.
Is that the ln of 2?
Say again?
Is that the log of 2, or is the log 2 squared?
Log 2 squared.
Okay.
Yeah, and I just wanted to write out another example, because we're going to come back to this in a second, and that's the notion of a non-equilibrium steady state. So non-equilibrium steady states are states which are they're steady states, so things have stopped moving, but they're not in equilibrium. And I think the perfect example is if you have just a simple electric circuit where the resistance is dissipating heat, so Joule heating. Now, if you turn this on, as soon as you turn it on, right, there's going to be, as soon as you turn the battery on, there's going to be some charge flowing around here. And so, things are going to wiggle around and so on. But then eventually this is going to reach a steady state. But this steady state is not in equilibrium, at least as long as there is energy in the battery, right? So if there is still energy here, there's still going to be a current flowing. And so there's be a constant production of entropy. So in cases like this, we would talk not about entropy production, but about entropy production rate. So how much entropy is being produced per second. In this particular example, this is just the Joule heating E² over are divided by temperature. So this is a famous result, which is coincidentally also due to Landauer. Just that the entropy produced in a RL circuit. Okay. So what I kind of wanted to start the story was historically. So it started with Clausius and the basic laws of thermodynamics. But now we start moving to different scenarios, and we have to understand how the thermodynamic changes when you go to scenarios which are different from the standard textbook thermodynamic scenario. So we saw this video before. This was a video that was clearly being played backwards. And in a macroscopic system, things always happen in one way. So there's a very well-defined arrow of time. So heat always flows from hot to cold, for example. If the system is microscopic, then heat will usually flow from hot to cold, but sometimes it may not. So we played around with this. This is something that a lot of people have studied over the past 2 decades. And I just want to show you some experiments to illustrate this idea, where we discussed this in the context of spin chains. So imagine you have 2 spin chains like magnets, and we prepare one hot, one cold, and then at t equals 0, we just connect them and let them go. And so we're going to see some spin excitations moving from one system to the other. And we can actually compute the entropy production. So we compute the entropy production from this. And what we find is that the entropy production is now a random variable. It fluctuates. So each time you repeat this experiment, you get a different value of entropy production. And so we can build a histogram out of this. And we can build a distribution of entropy production. And this is shown here for different sizes of the spin chain. So what is important here is that when the sizes are very large, you see that this part here, which is the probability that you obtain a negative entropy production, becomes very small. When the size is small, it's a mess, right? So if the size is very small, it's a complete mess. But as the size starts to increase, you could maybe even call this region a violation of the second law, in the sense that you're observing a negative entropy production. You see that the probability of obtaining these violations becomes smaller and smaller. And so that makes sense, right? So this shows a transition from the micro world to the macro world. As you increase the sizes of the system, you observe more thermodynamic behavior. And this is also related to the famous fluctuation theorems, which maybe you've heard of. By Chris Jarzynski and also Gavin Crooks have a series of very famous papers which show, and this is, I think, the most remarkable thing about all of this, that this probability distribution has a very special symmetry. The probability that you observe a negative entropy production is actually related to the probability of observing a positive one by an exponential. And so this means that, if sigma is a very big number, the probability that you observe, p to the minus sigma, sigma being big, is exponentially suppressed compared to the positive one. So this tells you, this is how you observe that large entropy productions should always be positive, and you should never observe large negative entropy productions because they're exponentially unlikely. And just this symmetry also implies that on average the entropy production is positive. So now we have a reformulation of the second law by saying that it's not the entropy production that is positive, it is the entropy production on average that is positive. And this is a generalization of the second law. Sorry, go ahead.
This fluctuation theorem, does that only apply for a small region of sigma? Because if you look at these Gaussian shapes, you get sigma big and then sigma y small, then it's not going to work. This equation.
Right. No. So this is the interesting part. So this applies across all scales, but they're not really relevant in the macroscopic world because precisely of this exponential suppression here. If you try to apply this for, like a gas or a macroscopic system, this P of minus sigma is going to be super tiny, like absolutely, very, very small. So that's why in kind of everyday world, we don't really observe these violations of the second law. We don't really observe this. This is a system of 200 spins, and you can imagine if this is 10 to the 23, then, this part is just going to shrink down. So, but the theorem itself is completely general. So it works across all scales. Okay, so now that we have this idea of entropy production, not as a number, but as a random number, something that fluctuates, we can actually go back to how we started in terms of defining entropy production as a comparison between a movie being played forward or a movie being played backwards. It actually turns out that the entropy production can be defined as a log of ratio of probabilities. And this is a very deep result, which go back to the 90s by several authors. Essentially, the entropy production, you need to compare how likely it's a forward process or a forward trajectory. I'm just illustrating a random trajectory here. And you need to compare this with the video being played backwards. So what's the probability of you observing something being played forward versus the same thing being played backwards? And the ratio of this, you take the log, this gives you the entropy production. Now, if the reverse process is as likely as the forward process, you get log of 1, and log of 1 is 0. So there's no entropy production. And so this essentially quantifies how much the forward and the backward process are deviating from each other, and this gives you the entropy production across each trajectory. Okay, so that's one way to go, is to talk about entropy production for small systems that fluctuate. And the other thing we can now introduce is quantum. So what happens if your system is quantum mechanical, and so also microscopic. So we've been working a lot on this, and I would say this problem of formulating entropy production for quantum systems, I think to a great extent kind of defines all of my research, even though I do other stuff. But this is really something that I've been really invested in. And I want to give you one illustration of how this works for a very simple system, but which is also quite general. I want to consider the following problem. Suppose you have a system connected to a bath, right? So just one bath, no hot and cold, just one. Now, okay, so this is the only slightly technical aspect here. So the system and the bath, they can be characterized by density matrices, rho S and rho E. And they're going to interact according to some Hamiltonian. So there's going to be some unitary interaction here between them. And so essentially, when you put your system in contact with a heat bath, this will start with rho S and rho E, and the unitary is going to produce some correlated state rho S, right? And now this thing is something that you might see for, if you're trying to play with two qubits or two, like a qubit and, electromagnetic fields or quantum systems. But if you think about it, this dynamics is actually quite general. Even, if you have a frying pan and you put it under the sink in the cold water, this is still going to be given by exactly this kind of formula. There's going to be a density matrix for your frying pan, a density matrix for the water, and a horrible, horrible, horrible unitary describing interactions between them, which I don't even want to start to imagine how it would look like. But it will still, at the formal level, be given exactly by this. So this kind of setup leads to a very, very nice formulation of the second law for quantum systems, which I particularly love, which uses information theory. And essentially, one can show that the entropy production for this process is a sum of two terms. One term, this I here, is what we call the mutual information. It's a measure of correlations. It's a measure of the fact that, a system interacts with the environment, they become correlated. Can be classical correlations, quantum correlations, that does not matter. But what matters is that they become correlated with each other. And the second contribution is what we call a relative entropy. It is a measure of distance. So it measures how much we pushed the environment away from equilibrium. So, because the environment interacted with the system, it was pushed from equilibrium. And this is a second contribution to the entropy. Yeah?
Is that the cohort Weber?
Yeah. The quantum one, but yeah, it's pretty much the same.
Right, because that's not really a distance, that's a divergence.
Right? Sure. It is a distance. Yeah. I mean, it is a distance in the sense that it's non-negative and zero if and only if they're equal. But you're right, it is not a proper measure. Yeah.
And it really picks up on like differences in the tails of the distributions. I don't know what that translates into quantum mechanics, though.
I think you can have a similar contribution, plus some additional terms related to like non-diagonal elements of the density matrix. But you have exactly that plus like some other contributions. Yeah. So this leads us back to this operational interpretation of irreversibility. Why is a process irreversible? It is irreversible because there's stuff that you cannot really control. There is no aspects of your dynamics that you don't really have access to. In particular, if you push your environment away from equilibrium, it's done. You cannot control that. Just like when the coffee mug fell and you dissipated heat, that heat is gone, right? That heat went to the environment and you cannot retrieve it. What I find super interesting is that there's not only this idea of pushing the environment away from equilibrium, there's a heat that flows to the environment, but there's also a contribution associated to correlation. You know, when the system interacts with that environment, they become correlated, and this correlation is gone. I mean, you can never retrieve it, right? So it's just something that is irretrievable, and so this also contributes to the irreversibility. Yeah.
So that first term, the mutual information, that's at least like the classical information theory. That's also the Colloquium divergence just between the product distribution and the joint distribution. So like the rho S tensor product rho E, the Colloquium divergence of that with rho prime SE is the mutual information.
Yeah. So this is also true
mechanically. Is that still true?
Yeah. So but there's a catch. You're absolutely right. You can also write this as a Colloquium divergence, but it's between this state and its reduced state, so it's marginals, which are not the same as these ones. Right. So you can still write it as a relative entropy, but not between this and these guys, but between these and its reduced states. So it's a bit different. But you're right. Yeah.
Okay. There seems to be like a loss of symmetry between the system and the environment, because you could always change the roles of the two, right? The environment is the system, and the system becomes the environment. Does that seems to not have that symmetry though?
Right. So that's a perfect question. Thank you. Yeah. So this formula is asymmetric, right? So there is the system and the environment are not treated in equal footing, and this is again an operational interpretation. We assume that we have access over the system, but we don't have access over the environment. So, you know, it's really, I mean, you could have a situation where you don't have access to both of them, that would be okay. But here it's assumed that, you know, you can still control the system. So you can still apply unitaries or revolutions to the system, but to the environment you cannot. So it's really you're postulating that. And that's what makes an environment an environment. So is Joe here? Oh, you're there. We had similar discussion, I guess, the other day about, you know, what makes an environment an environment. You know, this could in principle be just, you know, a qubit, but what makes it an environment? This is really an operational formulation. You're saying that for whatever reason, you don't have access to it. So whatever happens here, it's done, right? So you can never kind of repair the damage. You can think about it this way, like something happens and then you regret it and then you try to bring it back. But your tools, the tools at your disposal, if you have tools to manipulate both system and environment, then you can bring it all back. But if you only have access to the system, you can never bring the whole thing back, right? It's irreversible. So that's kind of the idea.
Gabriel, is this totally universal, or is this impossibility associated maybe with me, but not with you?
I can imagine that that could be possible. Like, you know, in a given experimental setup, maybe someone has access to this. In another one, maybe no, they don't. I can imagine that being possible. It is true, though, that, you know, as a system grows in size, as we usually think that environments should be big. So as a system grows in size, our ability to control it, you know, diminishes exponentially. So, you know, 1 qubit you can control, 2, 3, you know, 100 probably not, 10 to the 23 definitely not, right? So there is this also asymmetry with respect to the size. You know, for a macroscopic bath, it is very unlikely that anyone would be able to control it. That's why it's a feedback. Cool. Yeah, there's also another issue that I just wanted to mention. You know, there has been a lot of discussion in the literature about how do you formulate this problem if you work with master equations. So master equations, I'm going to show you a couple more in a second. They're just effective ways of describing the heat path. So, you know, we can't really model the heat path because this requires that we have knowledge of the entire degrees of freedom of the path, which we seldom do. So we like to use effective descriptions of the path. And we do this with the so-called master equations. And there's been a lot of discussion that master equations can violate the second law. So you have many papers saying, master equations violate the second law and so on. And there's been a almost 10-year debate in the literature about how to formulate the second law for master equations. And this is something that, it's now pretty much resolved. So the resolution are in these two papers, but it's still an ongoing discussion, but I would say it's 95% resolved. And I just wanted to kind of point this out. Okay. Yeah, so let me now just try to give you an idea. I see that I'm already running out of time. So let me just try to give you one idea of how this can actually be applied. So suppose you have, again, a system interacting with a heat path. Now, you can imagine your system is an atomic system, has energy levels. And what we imagine is that if you couple it to a heat path, there's going to be some stochastic jumping up and down. So the state of the system might jump. Suppose the system starts in a highly excited state. It's going to jump up and down. And in the end of the day, it's just going to keep jumping stochastically, depending on the temperature of the environment. So the environment is going to make your system jump up and down. But this is the classical picture, but there's a fundamental new feature when you go to quantum systems, and that is quantum coherence. So in addition to the populations of your system changing, any superpositions will also be damped, right? So this is the process we call decoherence, the destruction of coherent superpositions due to the environment. And one of the nice features about this entropy production is that it can actually be split into two contributions. You have a contribution which is a classical contribution associated to the populations of your energy levels. And you also have a contribution which is an entropy production due only to decoherence, due only to the laws of coherence. And this is cool because it means that you can actually produce entropy without having any heat flow. So you can have dissipation of information without having dissipation of energy. And in classical systems, this is never the case, right? So we saw that entropy production in classical case was always the heat divided by temperature. So you always had this heat flow associated to entropy production. Here, no, you can still have, even if you have no energy dissipation, you can still have dissipation of information.
So, is this a consequence of like that type of master equations? So you never get interferences between population and coherence terms?
That is a very good point. Yes. The fact that we can split it like this, it's true. It's for specific classes of not only master equations, but other kinds of processes where you get this non-interference between them. Yeah, that is a good point. Yeah. Okay, and I'm gonna just show this last application, which is so we saw before this inequality. We had before sigma larger or equal to 0, and sigma was the product of these changes in temperatures with the heat. And I emphasize that when this was 0, it meant that the sign of Q should match the sign of this gradient in temperature. But what happens if the systems have initial correlation? So if you have a hot system and a cold system, which are initially correlated with each other, that in this case, you actually get a modification of the second law, which is pretty cute. It essentially says that the same product that you have here is actually larger or equal than the change in mutual information. So again, mutual information, this I, is just a measure of correlation between the systems. And this is a delta, so it's like a change, right? So what does this mean? Well, if you create correlations, which is usually the case, I mentioned, the system and the back, they interact, they create correlation. If that's true, then delta is a positive quantity. And so we have that the product of this times this is again a positive quantity. So the signs should still match. But if you consume correlations, which is unusual, but you can arrange it to be like that. So if you can consume correlations and make this delta negative, then you break this requirement to have the Q match the sign of the change in temperature. And so you can actually make the heat flow from cold to hot, right? So you can actually start with a hot system and a cold system, and in the end up with the cold system colder and the hot system hotter. And of course, there's nothing super special about this. I mean, we do this in the refrigerator every day, right? In the refrigerator, you make heat flow from cold to hot, that's fine. But you pay a price to do that. You use electricity, you use a fuel in order to make heat flow from cold to hot. And here, I mean, the interesting thing is that, information is actually a fuel. For an energetic flux, we can actually consume, so consuming meaning delta I negative, we can consume it to make a heat flow from cold to hot. And we have some, we did an experiment on this.
You have a question here, so I mean,
Oh,
how are
yeah,
you changing the correlations over here? So I mean,
sorry, say again.
so you have a system and environment, right?
Yeah, yeah.
So I mean, how exactly are you changing the correlations? Is it the environmental thing which is changing the correlations, or are you modifying the system itself? In which case, doesn't your operational definition change?
Right. So what we're considering here is a scenario where you initially prepare one cold, one hot, and then through some kind of process, you make them correlated. So you make them interact. So they're still so it's like this. Locally, if you look at this guy, it would be hot. If you look at this, it would be cold. But little do you know that if you look at it globally, they're actually correlated with each other. That's the idea. But you have to produce that.
So you prepare the system in that initial.
Yeah, exactly. And of course, you can go into the question of, there's going to be an energy cost for preparing this, and that's absolutely true, right? I mean, there's no free lunch here. Yeah, yeah.
Can you comment on Landauer's principle in this case? Because if you're destroying correlations, that would be equivalent to erasing information, which has an energetic cost. Right, but here it seems like you're increasing the temperature difference, you're gaining energy from it. So is this a like maybe I'm not understanding how Landauer's principle is
right
relevant.
Right. So I think that's a very good question. I'm not sure I'm going to be able to give you a very satisfying answer. I think this is how the logic should go. Here, I mean, Landauer's principle is about an external system, which is erasing some information of your bit, for example, right? Here, there's no external system. It's just the two of them together. And you're not really erasing information. You're just exchanging correlations between them. So I think in that sense, it's
Not an erasure.
Yeah, it's not an erasure. It's not like an external, thing that is erasing your information. As I said, maybe that's not the most satisfying answer. But yeah, so this is just an example. We did this with NMR, and we had two scenarios, uncorrelated and correlated. And you see that in the uncorrelated, this is heat, so energy flow. You get cooling, so would be the energy of the hot system, and the energy of the hot system goes down, so heat flows from hot to cold. If they're correlated, then it goes up. And what's interesting is that we see that as it goes up, this is the mutual information, and the mutual information goes down. So it's really, it's like that. You're consuming your fuel, your mutual information fuel, to make heat flow from hot to cold. Okay, so I think I'm already. When did we start? 3:45. Okay, so I maybe 10 more minutes. I guess it's okay, right? Okay. So let me skip this part. And let me move on to some of the more recent things that we've been working on. So imagine you have a microscopic system, and this applies to classical or quantum. And imagine that you have a current. Now, current could be like a particle current if you have like a quantum dots, in condensed matter, like electron currents. It could be heat currents, work currents, and so on. If you go to the microscopic scale, then these currents start to fluctuate. We discussed that, how thermodynamic quantities, they fluctuate. And so if you plot your current, it's going to be something noisy like this. In 2015, Andrea Barato and Udo Seifert in Stuttgart, they proved a very, very curious and very interesting relation, which they called the thermodynamic uncertainty relation. It has nothing to do with Heisenberg's uncertainty relation, even though the name might be confusing, but that's what they call it, the TUR. And the TUR is a simple and elegant inequality describing the variance of the current. So, how much the current fluctuates. This is like the noise to signal ratio, right? It's the fluctuations divided by the average. And the bound says that this ratio must be larger or equal than 2 divided by the entropy production rate. And this is actually counterintuitive, at least in my opinion, because it means, since the entropy production is in the denominator, it means that if you want to reduce your fluctuations, if you want to make your device fluctuate less, then you actually have to increase dissipation, you have to increase your irreversibility. And we learned that, reversible processes are good and irreversible processes are bad. But if fluctuation is an issue, this is not true. You can actually have, you increase your dissipation to actually reduce your fluctuations. And this could be important, like for example, if this is an electronic device, you don't want it to fluctuate a lot. It might, just fry or something, or just get wasted. And so you really want to reduce your fluctuations. And to do that, you must increase your dissipation. One absolutely beautiful consequence of this is the following. Suppose you have a heat engine, and you look not at the work, the average work, but you look at the variance of work. Now, the variance of work, it can be written, this is, with a bit of manipulation, it's a direct consequence of the TUR. It can be written, it's larger or equal than something which depends on this ratio. So there's efficiency here divided by Carnot efficiency minus efficiency. And so this shows that if you want to operate your device very close to Carnot efficiency, your fluctuations are actually going to be huge, right? So you don't want a device operating in Carnot efficiency. Carnot efficiency is bad because you're going to have huge fluctuations, right? And so I think this is a really, really powerful and elegant inequality, which shows you how it gives you strategies to try to reduce fluctuations. And it introduces fluctuations as like a new element in your thermodynamic analysis. When we do talk about thermodynamics, we talk about heat and work and ta. Here we have a new element, and that's the fluctuations of heat, the fluctuations of work. And that might be important if your device is microscopic. Yeah.
I have a question about the interpretation and whether it's intuitive or counterintuitive. Actually, it's something I haven't wrapped my own head around. So I want to hear your thoughts, right? So is it really counterintuitive that you must increase dissipation of the curve fluctuations? Because if you're dissipating a lot of heat, reducing the number of accessible states in your system. If you reduce the number of accessible states in your system, you have less fluctuation.
Yeah, I guess so. I mean, you have a very good point. I don't have a good counter argument. For me, it is a bit counterintuitive, just in the sense that we're used to thinking about irreversibility as something good.
Right.
But you have a very, very good point. Yeah.
I'm just going to give another example where it's probably not counterintuitive. So if you take a classical fluid and you have turbulence, more dissipation makes the flow. If you're interested in reducing turbulence, more dissipation will reduce the turbulence, which is a good thing.
That's
Smoother flow.
That's a very interesting example. I never thought about it that way. You're absolutely right. Yeah. Okay, so cross this one. Not counterintuitive.
Well, intuition is relevant, right?
Exactly. There's also another bound, which I think is quite interesting, that was discovered in 2018 called the kinetic uncertainty relation. And this is a bound which has almost the same structure. It looks very similar. But the thing on the right is not related to the entropy production. It's related to a new thing called the dynamical activity. Now, the dynamical activity is essentially the number of transitions, stochastic transitions in your system per unit time. So these bounds, they were developed a lot in the context of biological physics as stochastic processes for biological physics. So imagine you have, this system being like a cell that is undergoing some kind of, transformation, producing ATP or something like that. Right, and you have these stochastic transitions. And the dynamical activity is just telling you how active the system is. And again, this bound gives you the same logic. It tells you that, the fluctuations depend, if you want to reduce the fluctuations, you must make your system more active. So it's, similar intuition. And this is just one example of the two bounds. So there's one here in this line and the other one in this line for one example system. And there has been very, very recently this year a unification of the two of them. So you can actually write the two bounds as just a single one. And people are quite excited about this because they're very pretty bounds and they seem to touch on some very fundamental physics. But there is a caveat, and that is that they're violated in quantum systems. So these bounds, they were proven strictly for classical systems. They required the laws of classical Markov processes and so on. And if you just try to apply them for quantum systems, they are actually violated. One example is quantum dots in condensed matter. Here I plot, the quantities in the bound in such a way that Q is the classical bound. So if it's above Q, it's fine. And you see that it can go below. Sometimes it's just a little, just a little bit below. Sometimes it's a lot. But these bounds can be violated in a quantum regime. And this leads to a very interesting question, which is why, right? Why are they violated? One particularly important example is thermoelectricity. So there's a lot of research in quantum thermoelectricity. I'm actually going to skip this just because of time. But why is there a violation in the quantum regime? So of course we think this is related to quantum coherence, right? So there's something quantum happening there that we don't really understand, which is causing these violations. But what is that? So that's the fundamental question. And perhaps as important is, is there any other bound? So is there a quantum TUR? What limits precision in the quantum world? What limits fluctuations in the quantum world? These are open questions. These are still not known. We recently carried out a very detailed study in a double quantum dot system. Let me just show you some pictures. So yeah, so this was the paper. And we carried out a very detailed study on this platform because this is something that you can do in the lab. You can actually, do experiments with this. And the question we're trying to ask is there any relation between these TUR violations and entanglement? Because we always think that entanglement is very quantum, and that's the first thing we want to look at. And entanglement is a consequence of quantum coherence. So it does make sense that if there's a lot of entanglement, the system should be more quantum, and therefore, you should have more of these TUR violations. And so we carried out a very detailed analysis. We looked at a bunch of models for this, just analyzing all possible parameter regimes and so on. And let me just show you the results. So what I'm plotting here is just two parameters. So the model has many parameters, which just to plot just two here. And this blob over here is what we call the concurrence, and that is a measure of entanglement. So when this thing is not zero, the state is entanglement. So for example, here it's not entangled, here it is entangled. This V, which is this red one, is a violation of the TUR. So whenever the TUR is violated, we plot it as a blob. And this other one is a violation of the KUR. And what we see is that actually they're pretty much unrelated, right? So whenever one is violated, the other isn't. I mean, there's some overlap, but overall, there's pretty much no relation. And we studied this for quite a few variations of the model and quite a few models, and there doesn't seem to be any particular connection between TUR violations and entanglements. There's also another picture here, just to showcase that. So these are just different parameters, different regions, and you see that overall there is really no relation between TUR and KUR violations and entanglement. So our interpretation of this is that even though everything is quantum coherent, there's a difference between what is a static coherence, which is entanglement, is a property of the state, and dynamical coherences, which are related to transitions, to transformations in the system. But overall, if how to describe this, I think it's still an open question. How to relate these TUR violations to a proper theory of coherence. So I'm going to stop here. There was this other part, which I think I'm going to skip because there's a lot here. And I'm going to go to the conclusions. I just want to say one thing. So here, our take-home messages. I just want to say one thing. A lot of what I described, especially in this last part, is actually in this paper that is going to appear in the archive maybe in 2 weeks from now, hopefully. And this is supposed to appear as a tutorial in PRX Quantum. So I've been working as a editor for PRX Quantum for a few months now. And there we have this mode of publication called a tutorial. A tutorial is meant to be a pedagogical paper, pretty much similar to the American Journal of Physics, but meant for PhD research. So I love the American Journal of Physics, but it has this problem that it's always meant for undergrads. And there's really no, or at least not that I know of, good papers for good journals for putting pedagogical papers, but at research level. And so this is one that I've been working on this like mad for the last 1 year, and I'm very happy with the results. So it should appear on the archive very, very soon. And that's, I think, all I had to say. Thank you so much for the attention.
Thank you so much for that. I have Zoom here, so if questions online, right? But any questions from the audience? I wanted to go back to that idea of the erasure part, because that is a really kind of stunning result that you can get rid of, that the correlation, that information is energy, right? And so biological systems apparently use this a lot, all the Maxwell demons that function in biological
You mean
systems.
this one, sorry?
Yeah,
Yeah.
yeah. So so like with Maxwell's demons, where a biological molecule is using fluctuations and somehow is extracting information in order to get the right result out of its fluctuations. There, I guess I just want to again sort of ask this question: why is this different from that? So I guess in that system, you've got the entire cell, the whole cell, and the macroscopic stuff in the cell. But here, there's really, you're saying that the fluctuations, or sorry, the correlations you're destroying are not being. There's no force from outside.
Right. Yeah. Yeah. Yeah.
So the correlation's just what I guess. So in this case, what is changing the correlation?
Right. So what's changing the correlation is the dynamics, right? Is the fact that just like when two systems interact, they entangle. They can also disentangle when they interact. So it's not always going to be like that. You really have to kind of tune the way they interact. So because this is a bound which tells you that this can happen, but it doesn't mean it will happen. So
right.
Depending on the way you make it interact, you can actually have this delta I to be positive. But if you play with the interaction, you can actually make it so that they disentangle.
So it's an internal dynamics, not an externally forced.
Exactly, exactly. And you could, of course, draw an analogy with Maxwell's demons. I mean, you can always think about the demon as being part of your system. So there is a bit of a matter of interpretation. Is the demon a part of your system, or is it like an external agent? And of course, you can formulate your laws in both ways, and they should be consistent.
Any more questions? If not, let's thank our speaker again.
Thank you.